iron chloride and H2O in equilibrium to give iron hydroxide, H3O plus, and 3 chloride ions. As a side, Fe3Cl3 would also be called what? Anyone remember? Iron trichloride is a Lewis acid. So you can review that bit too. This is a Lewis acid. Okay, so complete the following sentence. Increasing the pH of the solution will shift the equilibrium, and heating the solution will shift the equilibrium. Okay, so you can see on the right, on the product side, we have H3O plus, which is your acid. So if you're increasing the pH, what's happening there is the concentration of acid going up or down when you increase the pH. Increasing, remember when you have a high pH, that means it's more basic, and you're having a low concentration of hydrogen protons or hydronium ions. So that means that increasing the pH is going to remove protons from the solution. And so what you're doing, if you increase the pH, is you're essentially removing product from this system. So if you remove product, which way does the reaction shift? If you take product away, it's going to shift to compensate for what you're taking away. So it's going to shift to the right if you raise the pH. Does that make sense? Okay. So we know it's either C or D because we're shifting. The first part is shifting to the right. Next part is if we're heating the solution. So the key word here is right here. This solution is endothermic. If it's endothermic, that means when you go from products to reactant or reactants to products, it's getting cold. So if it's doing that, that means you can put heat on the reactant side. And if you're adding heat, so you're going to essentially be adding reactant now, putting more reactant into the equilibrium, that's going to shift to compensate to make more product, and it's going to shift to the right again. So then the answer here is D, to the right and to the right. Can I clarify that a little more for anyone? Okay, you ready?
Yeah, I think so.
All right. Yeah.
Do you think you could dim the lights a little more?
In the
It's just hard to see this one.
no, but we're gonna do it front. So how do you turn off the front? Okay. Is that better?
Yeah.
Okay. Just want to make sure you guys don't read your papers. Okay.
Okay. So this question right here is going to be another one about kinetics. We're going to have to use a formula Arrhenius equation. We'll get to in a second. So the isomerization of cyclopropane to form propene. This reaction basically has 3 carbons linked to each other that then forms propene. Follows first order kinetics. The rate constant at 700 Kelvin is 6.7 times 10 to the negative 4, 1/minutes. And at 760 K is 2.3 times 10 to the minus 2 per minutes. What is the activation energy for this reaction? So, if you need to relate 2 rate constants to each other with 2 temperatures, and you're trying to find EA, there's a particular thing given on the answer. Sorry, on the formula sheet over here. That's going to be your best bet. Oh yeah, we're given a bunch of questions. We're given a bunch of possible answers in kilojoules per mole. So we're looking for EA. You know, we're trying to solve for EA. We have 2 rate constants and 2 temperatures. So this equation right here, this ln K2 over K1 equals EA over R times 1 over T1 minus 1 over T2 is the best one to go with. This is related to the Arrhenius equation. It's basically derived from there, but I'm not going to go through that. So the Arrhenius equation for your reference. Is that actually? Should we bring it over here? For your reference, that's right. K equals E to the negative GA over RT. So we want to solve for EA, right? So we can rearrange this whole thing by multiplying by R over here, and then dividing by this term. So that's all pretty much I've done right there. And then after that, it's just a matter of plugging in the values we're given. So we had, right, T1. What if I do this in right here? Right, so we have T1 equals 700. First one we have T2 is 760. We were given K1 and K2. And pretty much we can just plug those numbers in and get a solution if you guys are not erasing on your calculators. Sorry about this. Oh, you know what? I wrote this down wrong. I'm sorry. This doesn't affect the answer, but it does affect one particular point of the answer. This is actually T2 minus T1. So basically what that means is that if you had those flipped, your answer comes out negative, and none of the answers are negative. So my answer is negative. That's what I'm So if you solve this, if you've done this on your calculators, if you happen to have one, the answer comes out as EA equals 260,662.26. Okay? I was using 8.314 for R, right? So 8.314, the units on this are joules per mole Kelvin, right? So my answer is going to come out in joules. If I use the 0.008314, right, then it comes out in kilojoules. So in this case, I actually have to take this and move it over here, and I get EA. I get EA equals 260.662. Now, if we go back and look at our possible answers, does everybody have this? Okay, we can move it. Go back and look at our answers. We have this nice answer D, 260. Any questions on how to use that modified version of this equation? Pretty much if you're given two rate constants and two temperatures, you're going to be using that equation. Yes?
Does it matter which order you put them in? Which one you choose is morning, which one you choose is two?
Yes. So it only in the sense that it matters which sign you get on your answer. Pretty much in general, I think I don't know if this is a rule overall. Not a physical chemistry. But you'll use the lower temperature one as T1 and the higher temperature one as T2.
Okay.
Is that right? What's that? Define T1 and T2. Low temperature one is T1, high temperature one is T2. There wasn't even this name. Is there? I don't know if there's a convention for that.
I think there is because you have K as the order.
Right, right.
Yeah, it's just how you define K1 and K2 and T1 and T2, and it'll work out.
Yeah. No, you're right. It should matter. As long as you keep K1 and K2 related, and T1 and T2, it shouldn't matter.
Okay.
Okay. So as long as you don't do what I did and write down the formula wrong, where you have T1 and T2 backwards, you'll be just fine.
Yep. I'm doing a molar solubility one.
Okay,
Which is
good.
an equilibrium one. I did that. I broke that one down too. Okay. Next one is about molar solubility. We're given to calculate this molar solubility of silver carbonate in a 0.1 molar solution of sodium carbonate. And we're given the KSP for Ag2CO3, which is silver carbonate. Okay, so we'll start by writing down the equilibrium equation. Ag2CO3 solid disassociates into 2Ag plus CO3 2 minus. Yeah. First write down that. Now, we have 0.1 molar silver carbonate, sodium carbonate, excuse me. And what we need to do is we need to find an